Hey everyone, welcome to this session as part of the Microsoft Student Summit Africa. This session I call Where Are All the Animals? It's all about using IoT in conservation and how we can take advantage of technologies like the Internet of Things to help protect wildlife. We lose one elephant from the planet every 15 minutes, and all this is driven by humans. Humans are leading us to lose one elephant from the planet every 15 minutes. And this is a really scary statistic. According to the International Union for Conservation of Nature, African elephants are on their red list. There's less than 400,000 of these beautiful creatures in the wild at the moment, and the rate we're going, we could lose every elephant within the next 10 years. This would be a shocking, shocking tragedy. This photo is one I took myself. It's of a magnificent bull elephant. This was taken almost 20 years ago. May not be the best quality picture, but it was the height of digital camera technology almost 20 years ago. And I took this at Sperming Island Game Reserve in Zimbabwe on the edge of Lake Kariba. Went there, went for a game drive, saw some absolutely stunning creatures, amazing elephants. Now the reason we're losing these elephants to humans is threefold. Firstly, poaching. People will literally go out and kill elephants for their body parts to sell. Also, elephants are migratory. They go from near the rivers in the dry season to where there's lush growth in the rainy season. And the routes they take, some of these elephants have been taking these for years, but humans are encroaching on their habitat. We are building settlements where the elephants want to go. And sometimes this limits the elephant's ability to get places. They know they need to go to a river, but they can't because there are now towns in the way and they don't know how to get to their water supply. Or if they do, they just want to go straight across where humans are, the humans will defend their land and fight against the elephants. Now we need to improve this. We need to live in a symbiotic relationship with creatures like elephants and all other creatures on our planet. So how can we do this? What can we do? This whole thing is a big problem. So how can we fix this? How can we protect the wildlife on our planet? And how can we do that with the power of technology? It's another photograph that I took. This was taken on the Okavango Delta in Botswana. We went out on a boat down the river and just watching elephants as they went through the river. They were swimming, throwing mud on themselves to keep the sun off. These are magnificent creatures and we don't want to lose them. So how can we use technology to protect our planet? My name's Jim. I'm a cloud advocate at Microsoft. I particularly specialize in the Internet of Things, so I'm here today to talk about how we can use the Internet of Things to track wildlife, monitor wildlife, and use this information to protect these beautiful creatures. If you want to get in touch with me after the session, if you've got any questions on anything I've talked about, do you want any clarifications, or you just want to talk about the Internet of Things, projects you've worked on, please feel free to reach out. I'm all over the internet at Jim Bob Bennett on Twitter, GitHub, Instagram, LinkedIn. I also want to leave you with this link before I kick off, aka.ms/GPS-tracking. This link will take you to a website that has got a whole lot of resources that you can use to recreate what I show off today. So one solution to the problem is GPS tracking. We can use GPS tracking to track wildlife, and that allows us to plan better, make better decisions, and know what's happening to the wildlife. If we can fit collars onto elephants with GPS trackers, we can know where the elephants are, and we can use that information to help protect them. Now, before we dive into actual GPS, the technology, and look at how we can use it in our Internet of Things projects, I do want to take a moment to talk about how we can define a location on Earth. Now, GPS data is known as geospatial data. So geospatial data is a location on Earth, and that's defined using three coordinates. We have latitude, longitude, and altitude. Now, altitude we're not going to really touch on today, but altitude is the height above average sea level that you are. What we are going to look at is latitude and longitude. So first of all, latitude. Latitude is lines that go around the planet, and it's all based on the rotation of the planet. So there is a famous line, the equator, goes to the middle of the planet, cuts through the northern part of South America, cuts through Central Africa, through countries like the Congo, and then cuts through parts of Southeast Asia, through Indonesia, places like that. And if you imagine the Earth as a ball that's spinning, which it is, it spins on its axis, the equator is a line that goes round the center of the axis, around the center of an imaginary line that goes through where the planet is spinning. So that's a line that's defined. And we define that as 0 degrees latitude. Everything is defined as degrees just how we measure a circle. If you use a protractor to measure angles, it's all based off that. And we have 0 at the equator. We define 90 degrees as the North Pole and minus 90 degrees as the South Pole. And then we divide the world up into degrees. Now each degree is roughly the same size. There's some slight variation because the Earth isn't a perfect sphere. It kind of bulges out a little bit in the middle due to its rotational nature. Now the way we measure this, there's two different types of measurement here. There's degrees, where you have a decimal value for degree. So you can have 12.7 degrees. You can also measure in degrees, minutes and seconds. And that's where you have a degree that's made up of 60 minutes and each minute is made up of 60 seconds. Now the other measurement is longitude. This is lines that go top to bottom. And so again, we have a 0 line, but because of the way the planet's measured, we actually have 360 degrees that go round. And so it's minus 90 goes through the middle of North America, or just to the side of North America. Minus 180 is the opposite end. 90 goes through China, the edge of India, and then minus 180 the opposite end. And if you think of this as the sphere, the 180 and minus 180 are basically the same point. And the same idea, it's degrees, decimal degrees or degrees, minutes, seconds. Now there is no point like the equator that you can define as the 0 point. So really somebody has to pick that 0. In the case of the Earth, for historical reasons, 0 is a line that goes through the Royal Observatory in Greenwich in London in the UK. And if you actually go to Greenwich at night, you will see a big green laser beam going through the sky. It's really nice to see. I've been on boats down the Thames at night, see this big green line, and that is the prime meridian. So they call it the 0 degree line, the prime meridian, and everything is measured based off that. Now, unlike latitude, longitude varies depending on where you are. So you've probably seen pictures of the world, maps of the world, looking like this one that we have on the screen now. But this is not an accurate representation of the Earth. This is what's called a Mercator projection. And somebody has taken the sphere that is the Earth and flattened it out. And to make it fit into this rectangle, they've stretched the North and South poles. Around about the equator, everything is the right size, but North and South poles, things are actually enlarged just to kind of make it fit on this flat projection. There's 4 red lines on this picture, 0, 90, 180, minus 90, 180, sorry, 5 red lines. These all actually join up at the top. So all these lines intersect at both the North and the South poles. So kind of imagine this has to be kind of squashed down onto a sphere. So that means when you're at the equator, each line of longitude is further apart than as you go away from the equator. When you reach the poles, all the lines actually meet. So the way GPS coordinates work is all based off satellites. There are loads of satellites all around the Earth. They have really, really accurate atomic clocks in them that keep track of time, and they send a radio signal out. And then you have a GPS sensor that detects the radio signal that comes from these different satellites. And then looking at the time difference between the signals from all the satellites, you can work out where you are from your sensor. Now, GPS has become the generic term for these kind of systems for measuring your location on the planet, but they're not actually GPS systems. The correct name is GNSS, a Global Navigation Satellite System. And a Global Navigation Satellite System is a constellation, a whole load of satellites that work together to help you find your location. The US were the first country to create such a constellation, unfortunately for military use rather than for the benefit of mankind. But this they called GPS, Global Positioning System. So that's where the name comes from. It comes from the US constellation. In the EU, they've released Galileo. Again, that's the EU constellation. Russia released GLONASS, and China released Baidu. And there's one from Japan and one from other organizations. So there's a number of these constellations in space that you can use for finding your location. Now this is a GPS sensor, more correctly GNSS sensor. And these sensors consist of usually 2 components. You have an aerial, and then you have a processor. Now the aerial, the antenna, connects to signals that come from satellites. And this aerial needs to have a good line of sight to the satellites. And then the signals come through to a processor, and the processor then takes that data and usually produces what's called NMEA sentences. NMEA is the National Marine Electronics Association, and that defines the standard for how they report location data. National Marine Electronics Association, because originally one of the first use cases was for tracking boats when traveling across the sea. And these NMEA sentences are streamed over a serial connection, and they contain information such as satellite information, the location calculated from satellites, the current time signal, things like that. This particular sensor is an Air 530 GPS from Seed Studios, and it works with their Grove ecosystem. And so it's all standard cables that you use to connect, all plug and play. You don't have to worry about knowing what cable to connect to what place. So I've got one here. This is a Raspberry Pi, and it's sitting on top of the Raspberry Pi is the Seed Grove base hat. So this is from the Seed Studios Grove ecosystem. It slides onto the GPIO pins of the Pi and allows me to connect Grove sensors from Seed Studios. And then I've got a UART cable. UART is a type of serial connection. I've got a UART cable that connects to my GPS sensor. And then I've got the Air 530 processor to produce the NMEA sentences. And there's the antenna there. It's a little blue light flashing blue to say that it's getting time pulses and green to say it's got a fix. So that is giving me data. Now this is currently on my desk, and getting a fix is not always easy when it's on my desk because it needs to pick up satellites. Normally when I'm working with a GPS sensor, I will fix it to my window, and that helps me get a clearer signal. But keep this in mind, if you're working with GPS, you need good line of sight to the various constellations to get a good signal. Now here's an example of an NMEA sentence, and this probably looks like gibberish, but this actually can be broken down into its component parts, and this gives you your location. There's multiple types of sentences. This to me is the most interesting one. It's a GGA sentence, and this means a position fix. This means we have got a fix from the GPS satellites. So the first part, $GNGGA, GN is the code for GLONASS. So I'm getting a signal from the Russian GLONASS satellites, and then GGA is indicating this sentence is a position. 020604.001, this is received at 6 minutes and 4.001 seconds past 2 o'clock UTC. So this is the time this message was received. Next two values are the latitude, 4738.538654 north. The first 1, 2, or 3 characters is the degrees. The last two characters before the decimal point is minutes, and the decimal point is the decimals of minutes. So this is 47 degrees and 38.538654 minutes north. So that is saying we're north of the equator. If I were to convert this to decimal degrees, it would be 47 point something, and that's north, so it's 47 point something. It's not a negative number. So we are north of the equator. Next two values, 12208.341758, W, that is the longitude coordinate. 122 degrees and 8.341758 minutes west. So we are west of the equator. We're now actually into the negative number territory. So in decimal degrees, this will be minus 122 point something degrees to say that we're going west. Next value after that, 1, says we've got a fix. So we have actually got an accurate fix. GPS sensors typically have batteries and remember the last location, so that if they lose a fix, they kind of know roughly where they are. But 1 says we have got a fix from a satellite. The next value, 3, says the fix comes from 3 different satellites. So let's actually look at a couple of demos of this. Let's look at this in action. So here I've got a bit of code that pulls data from my GPS sensor. And this pulls it over a serial connection. So when I connect my GPS sensor, it is a serial connection. I connect to it like any serial cable, and I can pull data off. So I connect to it. It's on /dev/TTY-AMA0. That's the standard for the Grove sensors. And I connect at 9600 baud. And serial data is just you pull out data character by character by character. And so I connect and I read lines, and then I print that line to the console. So if I just run this, you'll see this is connecting and this is putting out data. Now, I'm going to be 100% transparent here. This is faked data. I'm not actually streaming data from my GPS sensor on my desk here. Reason being is I don't want you to know where I live. That would give you the exact coordinates of my house, but that's really not a good thing to do. So this is simulated data on a trail around the Pacific Northwest. But this is the data you would get. You get more fields, you get various fields about satellite information, but right now the thing we care about for location is the GGA fields, and that's what's coming through here. Now, this is the raw data. This is not that useful as it is. You need to decode it. In the Python world, there is a package pynme2, and this can actually decode the NMEA sentences. So it takes the lines of data, and then depending on the sentence type, we can decode this. For every sentence we receive, we parse it. If it's a GGA sentence, we can get out the latitude and longitude. This always comes out as degrees, minutes, degrees and minutes. We can convert it to decimal degrees, and then we can make the adjustment. So if we're south, we need to make it a negative value. If we're west, we need to make it a negative value. So that can then give us GPS coordinates in decimal degrees. So if I run this, that will take the same data, and it's reporting the actual location, 47.52 minus 122, with data from 3 satellites. So this is decoding it using pynme. So I've taken my data, I've decoded it. Now I'm using Python, I'm using a Raspberry Pi. If you're doing this on Arduino, there are similar libraries that can decode these sentences. So we can put a device on an elephant, can use GPS data to gather this data, we can then decode it on our device, and then we can use that information. But how do we use this information? It's no good if it's just on the elephant. We need to know where that elephant is. We need to get that data up to the cloud somewhere. This location is no good if we can't do anything with it. Now IoT, the Internet of Things, people talk about it being its devices connected to the internet, but fundamentally it is about data. It's about gathering data from things, sending it to the cloud for processing. So we need to gather data from the elephant, send that to the cloud so we can do things with it. We can learn where the elephants are. Now one question that comes up a lot with dealing with IoT data is how much data, how often do we send it? Now, we probably don't need real-time tracking on an elephant. You'll notice if you're using like a ride-sharing app, you'll get updates on the car moving every few seconds. So in that case, you want to have data coming on a regular basis. With an elephant, we probably don't want to send data that often. Maybe every minute, every 5 minutes. Yeah, elephants can move quickly when they need to, but they don't run fast. So you can probably get away with sending data every 5 minutes, 10 minutes, whatever. We need people who understand elephant movements to tell us how often to send data. And ideally you want to err on the side of too much data rather than too little, but not to the point at which you have too much data to handle. It's kind of a very tough decision working out what the right amount of data is. As an IoT engineer, a data scientist can be your best friend. If you're gathering data, you need somebody who understands that data, understands the use of that data to advise you on what data to gather and how often to gather it. Now to get IoT data to the cloud, in the case of the Microsoft ecosystem, one of the best services to use is Azure IoT Hub. And this is a basic big fat pipe. It's like a big message system. Your IoT device will send messages to it, and then you can put services, cloud services on the other end to take those messages off and process them. And the hub manages all that connectivity. It manages the messages coming in, it manages the security of your devices connecting, it manages storing messages for a short period of time if you need to replay them, it manages connecting to cloud services, the cloud service can pull the messages off, it manages just how long your cloud service will be down for when they reconnect and can replay message data. They kind of track what's being received by each service, and it allows you to send messages back from the cloud services to your device. Should you need to send things like firmware updates, or you need to send a message to the device to say, actually, can you capture data more often, or can you do this, or can you do that? And you can control all that through IoT Hub. It doesn't really have a flash UI. It's not a software as a service platform. It doesn't have charts and graphs that shows you the data coming through. It's just this big pipe that you use to build your application ecosystem around. So let's have a quick demo. Let's actually look at IoT Hub. And as I said, it's not that interesting to look at. This is Azure IoT Hub inside the Azure portal. So the Azure portal is the user interface you can use for managing all your Azure services, and this is my IoT Hub inside this. I get a few charts around the number of messages that are being sent, so I can kind of monitor my service, but I don't really get any more than that. Now, in terms of connection, IoT Hub has security built in, and it's really important that you have security when you have IoT devices. We don't want poachers spoofing IoT devices. We don't want poachers hacking into our system. We have to have security. Now, the way IoT Hub does security is by managing devices with either a key or a certificate. So I can create a device inside the IoT Hub UI or through the command line interface or however I want to do it. I can create a device in IoT Hub and either have a key for that device, a unique key. I'll show you my key here. I can use a key, or I can use an X509 certificate. And then when my device connects, it says, this is me, here is my key, here is my certificate, let me connect, and IoT Hub lets it connect. Without the key, without the certificate, I cannot connect. So I get like a connection string here, I use this with an SDK, and this connects. It connects to this particular IoT Hub, this is the device ID, and then this is my magic key. Now, I can set this device up manually inside IoT Hub, or there's a service called a device provisioning service. And I can then, in the provisioning service, allow a device to provision itself, but the device still has to have that magic key or the certificate. So when the device connects, it says, I've got a certificate, I'm allowed to connect, please create it. And that will automatically create the device in IoT Hub for you. This is IoT Hub. Doesn't look like much, but it's incredibly powerful because of all the services you can connect. This is just an administration tool for it. If I actually show you some code, I'm going to run a Python app, and what this is exactly the same code we saw before that connects to the sensor, pulls out the NMEA sentences, decodes those into latitude and longitude, and then sends these up to the cloud via the IoT Hub. So my device, I'm using the Python SDK on my Raspberry Pi. It's connected to Azure IoT Hub. I build some JSON that's got GPS coordinates. I've got the latitude, the longitude, the number of satellites, and I'm creating a message that I'm sending to Azure IoT Hub. Now I'm sending every few seconds here just for demonstration purposes. You probably wouldn't need to do it more than every few minutes. Obviously, if I did this every 10 minutes, you'd see one message and yeah, it'd be a very long session. So this is now going up to the cloud. And what we can see in the portal, in a minute, we'll see that there's more devices connected. We'll see a jump in this chart in a second. If I refresh it, I might see it sooner. But then we see a jump in the chart, saying the message used and the connection. So we'll kind of see stuff in our monitoring here, but we don't really see much with our messages. So that's getting data going into our hub. Once it's in our hub, we have the question of what do we do with it next? So our architecture so far is we have a device connected to Azure IoT Hub. It's sending that up to the cloud. Now, before we kind of dive into what we do next with this data that's in IoT Hub, we need to consider our connectivity. We need to consider how we get this data from the device to the cloud. I'm at home, I'm using my Wi-Fi. You don't often get Wi-Fi in the middle of Africa, in the middle of the savannah. You don't get Wi-Fi out in game reserves. So you have to think about what is the right connectivity method for your device depending on where the device is. Now my phone has GPS on it and that connects over cellular or Wi-Fi because my phone's designed to have cellular. So we could do the same thing. We could put cellular connectivity on our device. Our GPS tracking collar could have 3G, 4G, 5G using cellular connectivity. And cellular connectivity can be really good, especially across a lot of Africa, the cellular connectivity can be excellent. So the photo I showed earlier of the elephants on the Okavango Delta in Botswana. One thing I noticed on that trip that I found really amusing is at the time that I was there, I was working in London, in Canary Wharf, which is one of the two big financial centres of London. Big skyscrapers, shiny new buildings, all very posh. And the 3G reception, because this was back in 3G days, 3G reception I got in Canary Wharf was terrible. 1, maybe 2 bars at the most. On a boat on the Okavango Delta, miles from anything, I was getting 4 or 5 bars of reception. The reception was better on the Okavango Delta than it was in one of the financial capitals of London. So you do get good cellular reception. So if you can use cellular, that is one way you can do it. Another way is LoRa, long-range connectivity. And this is based off radio waves. So you can have a LoRa transmitter in your device, and that can send a signal that can travel miles. Now, LoRa limits the amount of data you can send. Literally, it's the small packets. Literally, the packet of data with the latitude and longitude, that's kind of the limit of what you can send. But for our use case, it's perfect. So we can send that over many miles to a LoRa base station, set up LoRa base stations around the place. They can then retransmit over LoRa, and you can kind of build a mesh that then connects at some point to the internet through some kind of gateway and gets the data up to the hub. So really, the connectivity based on your use case, how you can connect. For my phone for GPS, I've got 4G, 5G built in, so I can just use that. But if I'm on a collar on an animal, I have to consider what we have available in the area. We also need to consider battery life. If I've put a collar on an elephant, I want this to last for years, just off the batteries. Maybe put solar cells on there, not so good because elephants like to cover themselves in mud to keep the sun off, so I need to think about the battery usage. Now, if I'm constantly connected via cellular, that would drain the battery. So ideally what I want is for my device to go to sleep, then wake up every 5 minutes, 10 minutes, whatever, make the connection and send the data, then go back to sleep again. Not continuously stream GPS coordinates, not continuously be connected, just connect every few minutes to save on battery. LoRa is usually really good for battery, uses a lot less battery than a cellular connection. So you have to kind of consider what the battery life is going to be. Okay, so we've got our data into IoT Hub. How can we store this IoT data in the cloud? Data is no good if we can't do anything with it. So we need to process it and store it. Now, one thing we can do is we can store our data to process later. We could process it on the fly if we wanted to, or we store it to process later. Probably what we want to do is store it and process later. We want to be able to build up maps of migration paths of elephants. We want to understand where the elephants are going. It's data that's gathered over multiple years potentially. So we need to store that data. Now, as I said, IoT Hub is a pipe. Data comes in as messages. So we can put something on the other end to pull those messages off and push those into storage. One technique for doing this is Azure Functions. And Azure Functions allows you to write blocks of code that are triggered by various different actions. One of the actions could be a web request, could be a database trigger, or it could be a message on IoT Hub. And so what happens is you can connect your Azure Functions to IoT Hub. When a message comes into the hub from your device, the function is called and is passed that message to process. Now, Azure Functions works on what's called bindings. You have input bindings and potentially output bindings. So you can bind IoT Hub as an input, and that way, every time a message goes to the hub, that message gets passed as an input to your function, to the code that you write. And then we could bind a database as the output. So when we return some data, it just gets inserted in the database for us. And we can bind that either as an output parameter. In our function signature, we can say, we receive the database as an output parameter and just insert rows into it. Or we can say, my function is going to return some data. The data return, I want you to put that straight into a database. So this binding makes Azure Functions really powerful. So let's do a demo. Let's just look at Azure Functions for responding to IoT events. So I've got an Azure function here. This is running locally inside Visual Studio Code. I can actually run this locally, connect this to IoT Hub in the cloud, test it all, and then deploy this to the cloud when I'm ready to go. And this is my function. And they're called functions because they literally are a function. I have a Python function called main, and this is my function that is called by the Azure Functions runtime when I receive an event over IoT Hub. I have a function.json. This defines my bindings. Just going to look at the input binding for now, but this is what's called an Event Hub trigger. Event Hub is a Microsoft Azure service that processes events. It's kind of like a message bus. IoT Hub is built on Event Hub. So I can use an Event Hub trigger to process IoT Hub events. And then when an event comes in, there's a parameter to my function called event, and that's an input parameter. And it connects my Event Hub via a connection string. Azure IoT Hub can expose an Event Hub compatible connection string. I use that here. I will show you that now actually. So in my IoT Hub, I have built-in endpoints, and one of these endpoints is an Event Hub. And so I use my Event Hub compatible endpoint, this one here. I use this string to allow my Azure function to connect. As well as this string, I can define what's called consumer groups. Consumer groups are kind of named connections. And so if I connect over one consumer group and pull data off it, I can connect over another consumer group and pull more data. So if I have consumer group A that's pulled 10 records off already, I connect consumer group B, B will go back and re-pull those same 10 records. It's kind of useful. Each service that you use to process data should connect to a different consumer group. So that way, if the service drops off and reconnects, it can restart processing data from the point at which it received the data before. So I have my connection string. Cardinality is 1, means I get one event. So you can have it multiple. So you can have blocks of events coming in one go. In this case, I want just one event at a time. And this gets from my functions consumer group, and it's a binary blob of data that comes in. So what this means is I can define a function with a parameter called event. It's an Event Hub event, and this will get called with every single message that gets sent to my IoT Hub. Don't worry about the return type for now. We'll talk about that in a minute. But what I do here is I get the body of my event, I log that, and then pull that out as JSON. So that pulls back the JSON that I get. So if I fire this up now, so this is running locally using the Azure Functions client tools, run this locally, and I would then deploy this to cloud once my development is finished. So start this up, give this a second to spin up, and you'll see it's now processing messages. It's now going through processing all the messages that it hasn't processed in the last few minutes since I started up my device, and now we're processing it. And you'll see we've got it processed an event that's got the latitude, longitude, number of satellites. So that's each event coming through. If I go back to my code here, you'll see every time this ticks, so 50744 482 50744 0482. So every time a message gets sent to the IoT Hub, it gets picked up by my Azure function. Now I can do whatever I want in this code. I could query, I could do some location things. I could use tools like Azure Maps to see whether or not the location that's received is inside a location or not, is inside something on the Earth. I can kind of do what I like to actually work out what the data is. I could process it, or I could just save it. In this case, I'm just saving it, but I could build whatever logic I wanted to in here. So this is the architecture we've got. IoT device sends a message to IoT Hub. IoT Hub then forwards that message on to Azure Functions where we process it. So the next step is storing it. Now, there's a lot of different options for what database you can use to store data. I'm picking Azure Cosmos DB for my particular solution for some very important reasons. Now, Azure Cosmos DB is a document-based database. It's not a traditional table-based database. It doesn't have tables and rows and columns. It stores JSON documents. Now, what's really cool about Cosmos DB is you can actually set it up with different APIs. So you can say, I want to have a Cosmos DB database that I query with a SQL-like API. So I query it with SQL as if I was doing a standard relational database, but it's going to be a document database. Or you can have a MongoDB API or a Cassandra DB API or other databases. So that way your Cosmos DB looks identical to another type of database. Now the main reason for picking Cosmos DB for me is it actually has spatial functions in the SQL API. So what that means is there's code I can call from the SQL API that allows me to query based off locations. So I can say, what's the distance between the location of the database and a particular point, or does this location fall inside this particular area? So I could run a query against my database to say, if I define a polygon, a shape on the Earth's surface that defines the outline of a town, have any elephants entered that? Have any elephants entered the town? If I define a shape that's out the edge of a game reserve, I can say, have any elephants left the game reserve? So I can run those space-based queries, run those spatial queries, and learn about how the data points I'm receiving, how they interact with various locations on Earth. And this makes this really, really powerful. Now, there's a whole lot of different storage options. You can just store data in things like Azure Storage, and then you can use tools like Azure Maps for doing those similar kind of queries, or I can just use what's baked into Azure Cosmos DB. So let's do a demo. Let's do a demo of this. So if I just go back to my Azure function, in my function JSON, I have an output binding. Type Cosmos DB. This says we're writing to Cosmos DB. Direction is out, so we are sending data out to Cosmos DB. The name is $return. $return special value. It says whatever is returned from my function, insert into the database. I've got a connection string from my database, and inside Cosmos DB, you have like an account which has multiple databases, and databases have multiple collections. So you can kind of think of it as in relational database terms, a database server can have multiple databases, and each database can have multiple tables. We have an account, multiple databases, each database has multiple collections. So this says, use my connection string, the animals database, and the locations collection. That's where the data goes to. Then in my code here, I build a record, and then I just return this. Literally just a return statement, returns a document created from a JSON blob, and this then gets inserted in my database. I don't have to worry about connection strings, writing any connection code, doing any manual inserts. This will just get inserted because I'm returning it from my function. Now this record has a GeoJSON entry in here. So GeoJSON is a standard way of defining GPS locations using JSON. I've got a location. This is the field my GeoJSON goes in. This is my GeoJSON. It's a point with two coordinates, longitude, latitude. It's always done as longitude, then latitude when you're doing GeoJSON. And you can have lines, you can have polygons. Polygon where you have multiple GPS coordinates to define the outline of the shape. Lines, two coordinates, start and end. In this case, it's a point. It's one location. The reason for inserting this as GeoJSON is this is the format that works with the spatial queries inside Cosmos DB. So this data is going into my Cosmos DB. If I now bring up my Cosmos DB database, I've got all my records in here, my locations, and each record, I've got the animal ID, which is a key I use to define which animal the collar is on, how many satellites send the data, and then my location with my coordinates. So that's stored as these JSON blobs inside my database. Now I can use these queries. I can take advantage of these spatial queries. For example, ST distance measures the distance between two locations. So I can say select out from my location where the distance from the location to a fixed point that I've defined here is less than 10 meters. If I run this, I get one result. So I've got one location in my database within 10 meters. If I increase this to 100 meters, I get 18 results. If I increase it to a kilometer, more 100 results so far, load more, up to 159 results. 10 kilometers, hundreds of different results. So I can use queries like this to help me locate my elephants. I can use this to say, are my elephants somewhere they shouldn't be? Are they getting too close? Is the distance to my polygon, distance to my town, if it's getting less than maybe 20 miles, do we need to consider relocating the elephants? So I can use this to track the animals. Once I've got this data, I can then use this to help protect them. I can say, yep, this animal has stopped moving. I can do a query on this. The location hasn't updated throughout a period of time. The animal's maybe been killed. Let's go out and have a look. Or we know we can plot a map showing all this data of the routes they take, and we know urban planning means we can't actually build in that particular area. So we've got this kind of great capability to analyze this data. As said, from Azure Function, you can store it anywhere. You can use Azure Maps to do this same kind of location-based checking. You can do things like geofences to say, is my elephant inside a particular area? Or we can do it from Azure Cosmos DB using the distance queries and the spatial queries inside the Cosmos SDKs. So this is our final architecture. We have a GPS device, connects to Azure IoT Hub using some form of long-range connectivity, whether that's cellular or LoRa. The messages from IoT Hub are then processed by Azure Functions, and we just write them straight out into a Cosmos DB database so that we can do spatial queries against that data. Now, if you want to recreate this yourself, if you wanted to build up this to monitor maybe domestic animals that you've got, or just where you're going in your car, or anything like that, you can put all this together, and all these Azure services are essentially free. All the SDKs for IoT Hub are free. IoT Hub, there's a free tier. You can process 8,000 messages a day. And when you reach the 8,000 messages, we just stop the messages coming in. So it's not a case of if it goes over 8,000, you pay. You say, I want a free tier. You're allowed one per subscription. You hit 8,000 messages, we stop processing messages. So that will not cost you anything. Azure Functions, your first 1 million function calls a month is free. You only have to pay a very small amount for storage because we're storing your files in the cloud, but it's essentially just a few cents for running your Azure Functions. And the amount you'll be processing, you won't be actually hitting any kind of paid levels on this. Cosmos DB has a free tier. So as long as you're not hitting it too hard, it'll be free. So the first time you create one up, there is a free tier discount you can apply that gives you a free Cosmos DB. So you can literally build this for only a few cents a month, which is really, really cool. It allows you to kind of try GPS tracking at home. And so yeah, I'm going to leave you again with this link, aka.ms/GPS tracking. Contains all the code we've done today, the code for reading from a GPS sensor, the code for decoding the sentences, the NMES sentences into latitude and longitude, sending that to Azure IoT Hub, Azure Functions code to then put this into a database. All you have to do is register for an Azure account, spin up the Cosmos DB, spin up IoT Hub, get the code going, and get connected. So we've done it. We've worked out how to build a system. We can use this system to protect wildlife. We can use this to build collars that we can use to track animals. And because of that, we can protect these amazing creatures from human damage. So go out there, check out this code, have a play with this, go out, think about what you could build, what you could do with this kind of technology, what kind of amazing solutions you can build that take advantage of GPS data that we can store, we can process, and we can use to help us make decisions to protect wildlife. So thank you very much for your time. As I said, I'm Jim Bennett, all available on the internet at Jim Bob Bennett. Please get in touch if you've got any questions on the session, or if you've built anything cool with IoT, please get in touch and share it with me. Enjoy the rest of the Microsoft Student Summer Africa.